Hello and greetings. In this video, I would like to present a demonstration of a feedback control simulator for liquid level control inside a tank. The simulator was built using Python programming language. It can be used to demonstrate the principle of feedback control, controller tuning, and fluid mechanics aspect of this simple tank system. The simulator is started by running appropriate Python command from the command line. Let's start first with the process description. In this tank system, a supply of liquid is charged into the vessel at a rate determined by the opening of LCV101 control valve. The liquid then exits the vessel via a long horizontal pipe attached to the tank base. Both the tank and end of the pipe are open to the atmosphere. The liquid level inside the tank is controlled by a feedback controller, directly controlling the opening of LCV101 control valve. The feed to this vessel can be varied by introducing a secondary flow into the tank to test the ability of the control system to reject process disturbance. Let's start the simulation by clicking the Start button. Now the simulation session has begun. You can see that the timer is currently ticking to signal away the simulation time. The simulation starts from an initial steady state condition, although it can be configured to start from empty tank condition. Currently, the liquid level inside the tank is almost 60% of its total height, and the flows into and out of the tank are equal, signifying that the tank is indeed in steady state condition. Let's open the controller panel to see the feedback controller setup. The controller is based on a simple PID system, excluding the derivative term as is normally the case for liquid level control. Using control valve that is air to open, the controller is set in reverse action, meaning any positive deviation of process variable from setpoint will result in decreasing controller output, in this case less liquid flow into the tank. The PID controller gain and integral time are arbitrarily chosen, although the parameters can be properly tuned based on the dynamic characteristics of the process and control loop. Let's increase the level setpoint to 70% of the tank height and see how the controller reacts to the setpoint change. Given the new setpoint value for the liquid level, the controller will adjust the valve opening of LCV101, in this case letting more liquid into the tank, to minimize the error between setpoint and process variable until the error diminishes. This is accomplished via a combination of proportional and integral action of the PID controller. This is known as setpoint tracking problem. You can speed up the simulation by adjusting the slider that controls the time speed of the simulation. Let's increase the speed factor to the max to speed up the simulation until the system stabilizes. Now that the system is stabilized, you can see that the flow into and out of the tank is at a new steady state value. Due to the increase of liquid level that acts as the liquid head inside the tank, the velocity of the fluid inside the pipe is increasing, thus increasing the fluid flow rate within the pipe. The level controller will simply keep the level at a setpoint value by charging the same amount of liquid into the tank. You can study the effect of process disturbance by introducing a secondary flow into the tank by opening valve BV101 and adjusting the flow rate value as you desired. For instance, let's set the secondary flow to 0.1 meter cube per second and see how the controller reacts to this process disturbance. You can speed up the simulation time to quickly reach the final steady state condition. Again, the controller is able to bring back the level to its setpoint value following a brief period of slight oscillations of the liquid level. Here, we can confirm that the total flow into the tank based on the primary and secondary flows is indeed equal to the flow out of the tank. This simply accomplishes the inventory control of the tank. To observe the recording of process variable as well as its controller output, we can open the strip chart recorder that shows the dynamic profile of these process variables in simulation time. Additionally, we can review the corresponding log data and even export a portion of this data for further analysis in an external data analysis program, such as Excel or MATLAB. This can facilitate system identification study for this virtual liquid tank system. This simply concludes the presentation of this video. In the next video, I will show you how the simulator can also be used to demonstrate the principle of fluid mechanics, particularly pertaining to the effect of fluid type, pipe dimension, and pipe material on the fluid flow within the pipe. Until next time, thanks for watching and have a great day.